Right, so I got an observation. I've got a really old laptop. Yes, I have got a really old laptop. So old that it doesn't have HDMI, and it turns out this is HDMI. So I've got to present for my iPhone tonight. Always have a backup plan when you do these things. We will see whether that's a good idea or not at the end, but it does mean that the interactive demos are going to be a little bit more difficult to achieve. Okay, so I need to start at the beginning, not the end. There we go. So this is about Swift Intermediate Language and about how that works under the covers. So some of you might not have seen it before. A little bit about me. My name's Alex Blewitt, Al Blue on Twitter if you want to send me questions or things afterwards. I wrote a book on Swift Essentials when Swift came out in 2014. I've recently updated it for Swift 2.x, and that came out earlier on this year. One of the nice things about writing about Swift is that it's always out of date. So I get to write that off. Actually, writing a book is not a good way of making money. It's quite fun, and you get to be able to say, hey, I wrote a book, but it's not a good way of making money. Still, fun nonetheless. So I'm going to talk a little bit about what makes Swift fast. I've got to be fast as well because I haven't got much time, and then I'll talk a little bit about Swift Intermediate Language. So Swift has actually been around for quite some time and has evolved really from essentially the love child of Objective-C and C++. It's kind of like Objective-C++ done right, throwing out way. If you look at the way languages have evolved over the years, they started off on, as everything does, from Smalltalk, and then it evolved through an object orientation, kind of going with the C++ Objective-C side of things, with the procedural languages like C evolving afterwards, and they've all sort of come together within Swift Swift 1, then Swift 2, and now onto Swift 3 as well. And the interesting thing about them is that there's a split between the dynamic languages and the statically compiled languages. So stuff like Smalltalk and Objective-C, all very dynamic. You could swizzle stuff on the fly. Swift is far more like C++ in that you can have a lot of static compilations and optimizations, but that have been merged down and still allow you to call Objective-C frameworks, which is, after all, where a lot of stuff like iPhones have gone. But there's been a lot of changes over the years in terms of how applications have worked. For example, we've seen speeds and desktops going up to, but then plateauing about 3 gigahertz. Mobile devices, they're about gig, 2 gig, something along those lines. But where we're seeing more performance coming on is more cores. So things really need to be able to work concurrently and really be able to work together. And the problem is that when you've got traditional languages that are essentially inherently single-threaded, it's difficult to apply that back afterwards, whereas Swift has been designed to be able to deal with that in a much closer idea. In fact, if we have a look at where the CPU has come from, back in the early days, we had 8-bit computers. They then evolved into the 16-bit computers, 32-bit computers as well. Had a Next Cube coming out in about 1990 or thereabouts. We've had the first Applebook coming along there. And the G5, I've still got one of these cheese graters underneath my desk. But what you're seeing is as the speed of these things has been going up, the actual bandwidth of the memory hasn't been going up anywhere near as fast. And that means although the processor can execute a lot of things faster, the bottleneck now is really being able to get the memory to the CPU to be able to execute data, rather than necessarily how fast the CPU can crunch through things. And in fact, recently we've had things like the Raspberry Pi, and indeed the Raspberry Pi 2, fitting into that sort of time. So it gives you a kind of an idea of where those things are. And we must remember, of course, that Objective-C started back in 1982 and then was adopted in the next operating system, which ultimately came on to be OS X and iOS that we all love today. So getting stuff in and out of memory is really the problem. Memory latency is where the significant bottleneck occurs because the CPU hits memory. If you're getting stuff out of registers, it's less than a nanosecond. If you've got something from the level 1 cache within inside a processor, and each CPU core has its own instruction and data level cache, there's usually a shared L2 cache per socket, and then an L3 cache that may be shared with GPUs or other CPUs of the same system. But being able to get data out of there is incredibly slow in comparison to how fast the CPU can actually work. And if you hit a cache miss, where you look for something but then you have to go back out to main memory to get it, it's a lot more difficult. I read something about the beer latency of hierarchy, where a register was beer in your mouth, a level 1 cache was beer in your glass, a level 2 cache was beer on the table, and a level 3 cache was beer that you needed to go to the pub to buy a pint for. There is really that much difference in terms of being able to get data out. And you can see when you look at the memory latency when you're accessing bigger and bigger memories that there's different steps as the memory gets further and further away inside caches. And that's one of the things that Swift is trying to do, because in Objective-C, back in the old days, we had NS array. And NS array was basically a bunch of pointers. And when you got something, you went out to a pointer there, and you went out to a pointer there, and you went out to a pointer there to be able to get your data. That's really slow. What you'd really like to do instead of having a bunch of pointers is have a bunch of data objects, and then you can just whack through them in a really fast sequential fashion. And that's why Swift arrays are better than NS arrays in terms of processing data. And a lot of these kind of decisions have sort of been baked into the Swift language. So Swift is really the sort of hybrid of static and dynamic languages to be able to go together. One of the things that you can do with Swift when you call a function is that you know you're going to be able to call that function. And so you can inline it at the call site. Whereas in Objective-C, everything's bouncing through Object-C message send, which under the covers boils out to be some sort of hash code lookup where you're effectively doing call whatever the cache of this function happens to be. And in fact, although Swift can generate Objective-C classes and use the runtime, for example, integrating into iOS frameworks, it's actually in the future going to be more efficient, because once binary compatibility is nailed down, allegedly in Swift 3.0, it's going to be a lot easier for that to be able to inline code and optimize it on the fly. Objective-C message send, you might have seen program crashed in Objective-C message send and thinking, hey, this is a really buggy program. Actually, no. Objective-C message send is the call holder by which all Objective-C things go through. When you call another object on a framework or another NS object, it goes through Objective-C message send and then bounces out on the other time. And this can actually take some time and some overhead. There's some registers. There's always registers for things like the CMD, which is the selector, if you're familiar with Objective-C, and the self, the instance that you're being able to deal with for every register call. Now, in 32-bit registers, CPUs where you had a limited number of registers, that was pretty bad. 64-bit CPUs have many more registers, and therefore you can be able to go through them a little bit faster. But actually, the amount of assembly instructions that you need to hit to be able to process each one of these things is actually non-zero. So it started off back in the day with about 107 back on Leopard. There was a bit of a drop that we had here where there was removal of special case GC. You might remember when Apple dabbled a bit with garbage collection. And then actually we've gone up a little bit for the later releases with non-pointer ISA support. But essentially, for every message that you send with an Objective-C runtime, you're going to hit these same 50 instructions over and over again, and that's just for one method call. And that's why Objective-C gurus will tend to tell you things like, don't call Objective-C messages repeatedly, or if you have something that you need to do a lot of, either vectorize it with a vectorization framework, or have a C function that does the same thing, because the C function can be unrolled a lot faster. Swift is also very amenable to optimizations. If you've got a function A that calls a function B, in Objective-C you can't really inline those because someone might swizzle out B and change it for something else at a later stage. Swift doesn't have that swizzling, so if you've got A calling B and you know that's always the case, you can actually then just join the two things together with optimization flags. And Swift is really quite amenable for a lot of these things in terms of understanding layout, figuring out which items that you load and access, being able to propagate those through to your programs as well. One other couple of things about that, it increases code size, which may be a bit of a downside, but by doing inlining, it can do optimizations. So if you've got a function foo that takes an integer, and if it's less than 0, you return immediately, maybe that's your error condition or something. When you call that with a negative number, Swift can not only inline the call, but it can figure out that -1 less than 0 can never be, -1 less than 0 is always going to be true, and therefore just optimize the whole function call away. And Swift is a lot more amenable to these kind of optimizations than before. But this talk was supposed to be about Swift Intermediate Language, and I guess I haven't got that much time left. So, Swift Intermediate Language and LLVM. LLVM stands for the Low-Level Virtual Machine, which is a really bad name because it's nothing to do with virtual machines. It's really like an abstract CPU processor. So in the same way we've got Intel x86 or ARM or Thumb, really LLVM is just a sort of generic instruction set for being able to call code. And the way that LLVM works and Swift works is that Swift compiles down to an intermediary language called SIL. That's really a runtime representation which is close to LLVM but not quite. And then it gets lowered one level further down onto LLVM, and then LLVM spits out all of the assembly code. Now, LLVM has been around for a long time. It's been powering the Objective-C builds since Objective-C 2.0, if you can remember that far back. And the guy who created LLVM, Chris Nattner, is also the same guy who created Swift as well. So, all good with that one. Let's have a quick look and see how they fit together. What you've got is the abstract syntax tree at the top end, which is really like a tree representation of your text code. That tree representation then gets parsed into what's called a parsed AST, so that's where all the bits are connected together and be able to join things up. That then gets compiled into the Swift intermediate language, and the Swift intermediate language is, as I said, this kind of generic instruction set for being able to represent Swift programs. It provides bindings to things on the local platform. So the way that Swift knows whether it's on a 32-bit or 64-bit platform is via a bunch of built-ins. And those built-ins are things like int64 or int2048 or some other kind of inbuilt function that is specific to the individual processor itself. That AST, that SIL rather, then gets lowered into IR, which is the LLVM intermediate representation. That's much closer to machine code, but it's still in an abstract set. And from the LLVM IR, everything is the same as it is with things like Clang. So that's been around for quite a long time. It's been optimized, and there's been various backends that have been provided for it. Now, what's particularly interesting about this is that there was a presentation done in October last year on the LLVM Summit, where a couple of the Apple guys talked about Swift intermediate representation and how cool it was, because then they could then have Swift representations that they could do optimizations on. You may have heard of Rust. Rust is a language that's also built on LLVM, and they thought, hey, that's a really cool idea. And now they have the Swift intermediate language for Rust, or as they call it, MIL, for the mid-range intermediate language, because they've got a higher and a lower range as well. But it does seem to be the way that LLVM languages are heading for. So I think Swift is really showing the way, not only for how to do Swift right, but also how to do other languages right. Putting that into graphics, because we all like lots of little wobbles. We've got here our print hello world. I would have print hello world, but it's been truncated, so it's just print hello for now. There we go. So that goes through the parse step. That then figures out that you've got a print function inside there. There's a string argument. Goes through the AST compilation, AST abstract syntax tree. So that's really just like a tree representation of that unit so that you can step through. The AST then goes through semantic analysis. So if you're calling something and it's supposed to be an integer, is it an integer of an integer type? If we're binding something, is that of the correct type, and so on? And then that comes out with another AST, but with decorated values on top of that. That AST, with all of that information, then goes through the process called SILGen. And what SILGen does is it takes your abstract syntax tree and then writes out a bunch of SIL-related concepts, the Swift intermediate language. And the SILGen is quite useful because not only does it allow you to see what the program code is doing under the covers, but it also allows for Swift-based optimizations to occur as well. So in Swift, if you know you're calling a function and it takes 2 arguments and you never use the value of the second function, the value of the second argument in the function, then Swift can actually then optimize that to effectively trim that out from the generated code. And there's quite a lot of optimizations that you can do at the Swift layer that you know to be the case and that you know to be easy to be able to implement, but that would be a lot more difficult once it had been lowered down to the intermediate representation layer. And then after it comes out of that optimizer, it goes into the IR gen. That then spits out a whole bunch of LLVM IR code, and that IR code then ultimately gets translated using LLVM into the backends that you're writing, whether that's a dynamic link library or whether that's a .o file or an executable file or whatever else. So that's the basic idea of the Swift compile pipeline. Now, this would have been of academic interest if we couldn't see each of these pieces, but actually what you can do is you can hook into each one of these different layers. I have an application called SIL Inspector. Was going to do a demo, not going to happen anymore. But if you search for AlBlue on GitHub and you get the SIL Inspector there, then you can download that and play around with it as we're going through this. If you don't want to, you can just follow the slides along. So, ubiquitous Hello World program. This one does say Hello World because we've got a slightly bigger amount of text inside this one. This is, of course, C because we've got the hash include inside there. And when you compile that with hello world.c and Clang, you can actually pass a parameter emit LLVM. Pretty badly named, should have been emit IR. But essentially what that will do is that will spit out the intermediate representation for your main program. And so in this particular case, we've got our private constant at the top, which is the hello world, null terminated, as all C strings are. Then we've got a main method that returns an I32, that's an 32-bit integer. And inside there, we've got a call function that calls puts, because I'm using puts to do the printout inside there. And then we return 0. We return 0 as a 32-bit int. So this is essentially LLVM, and that LLVM can then be translated into ARM code or into x86 or x86 64, or indeed a whole bunch of other different types afterwards. Here's what the hello world looks like if you're doing it in assembly. You can run emit assembly and then be able to compile that down. So at the top, we've got our main function. There's this really cool naming convention that they do when they're compiling things. They stick an underscore on the front of it. Dead cool. So we've got underscore main at the top there. There's some green stuff. Don't know how much the green stuff shows up at the back for you. But the green stuff is the stack management. The things like the push RBP, move RSP, RBP, you can kind of ignore that. That's there on all assembly functions. They just blend into the background after a while, kind of like comments. Comments? What are they? Yeah. Okay, the LEQ is actually loading the address of a string, so that's getting the hello world out into a particular pointer. We're then calling puts, again, that cunning underscore on the front of it so you know what's going on. And then we're just returning 0. There's something at the end of it, XOR EAX, EAX. If you take a number and you XOR it with itself, you get 0. And that's a really cunning optimization that assemblers use when they want to assign a variable 0. So on the right-hand side, that just means EAX equals 0, so that when your function returns, it returns 0. Exciting stuff. So that's what the assembly looks like. Okay, there is actually a relatively close comparison between the LLVM IR and the generated assembly code, which is then the thing that will get compiled for your platform. So what does that look like when we deal with Swift? It doesn't, because that's the next slide. The advantages of IR, the intermediate representation, are something that you can still be understood when it's compiled. So you can have a look at it, you can see what it means. You can, once you know how to read it, be able to read types into it, like I32 for the 32-bit int. Most of the time when it calls functions, those functions are defined inside there as well, and so they will go back again. You can inline. If you know you're calling puts and puts is never going to change content, then you simply suck the bits out of the puts call, stick it into your program, and then you've got a statically linked executable that isn't going to have any extra dependencies in there. You can do elimination of unused code paths. So if you've ever got something like you are doing an if test, and if an error occurs and the error never occurs, then you can simply strip out the error conditions of your logic. That's not so good. But you can remove things like if debug. Okay, so traditionally what would happen in C and Objective-C is you'd have an if-def debug, and that would simply hide a whole bunch of your code. In Swift, you can do if hash debug as well to be able to remove the code. But the elimination of unused code path works even if you've got a Boolean value and you just say if Boolean is false or true to be able to include the debug logging inside there. So here's what it looks like in Swift. We've got print hello world instead, slightly different name, but it still works the same thing. We do a Swift C with hello world.swift emit IR. And emit IR is the thing that will then print out the IR code for your particular function. And this is what it looks like. So we've got at the top, hello world, null terminated. Hey, it is C after all under the covers. Define at main, I32, I8 star star. So I8 star star is the car star star that you would see in a main function. And then you have something that is a complete load of gibberish right in the middle. Slightly above that because the alignment of the slide was off. The way that Swift translates things into Swift function calls is vastly different from C. It doesn't just stick an underscore, although it does begin with an underscore on the front, but there is a whole bunch of gibberish that's put on the front. And this is something that's called name mangling. The idea of name mangling, as I said with C, just stick an underscore on it. When you're dealing with C++, you put underscore and then a capital Z to indicate that it's come from a C++ name. The way that C++ decoding works is that you have a number followed by that many characters before you hit the next thing. So it's basically a run length encoding for being able to put the name together. So the way that we'd represent main in C++ is underscore Z for main. So for main is the length of the keyword main. And then IPPC, which is an integer and a pointer to a car. Okay, perhaps not particularly exciting, but that's the idea for name mangling doesn't just come from Swift, it's been around for a while as well. What does that look like in Swift then? Well, we've got a much larger string to be able to deal with, which is that one at the top there. And instead of beginning with Z, we begin with underscore T. So underscore T indicates that there's a Swift symbol that's coming up in your program, capital T that is. F stands for function type, SS, capital S, small s, stands for a Swift string. In fact, most of the things with capital S have specific meanings of the kind of things that you need to use a lot of in Swift so that they can compress it even further. 5 print, so that's print 5 characters long. And then something which is TGSAP underscore, which looks like complete gibberish, but actually what it is it is an array of a protocol type that doesn't have any generified types in it. So the P underscore is the protocol generic type, and then the T is a type of GSA, which is an array of, and then that protocol. Now, This has also got something called a separator and a terminator. There wasn't anything to do with a separator and a terminator in our function, so where did that come from? Well, it turns out that the way that you call a Swift function is that you have a new line character and you have a separator between multiple arguments that you might pass inside it. Those aren't there, those are default arguments, but they're still present in the function that you end up calling, and that's why they turn up in the mangled name symbol, even if we don't do anything. Because none of us can read that, unless we've got a slide handy to be able to read it from, there's a program called Swift demangle. And Swift demangle essentially takes a stream of data, and any time it finds something with _t on it, tries to translate that into a demangled Swift name. So if we either echo that string, or indeed if you take the output of something like Swift emit IR, you can just pipe it through Swift demangle, and it will replace anything that it finds inside there. And that's actually a lot easier to be able to understand, and we can see here that in this case, the function swift.print takes a protocol, an array of any's. So protocol angle brackets is just the type alias for any. The separator is then the string that you use at the end of it, and then is the string that you use when you've got multiple arguments inside there, and then the terminator is the thing that you put at the end. So that's how Swift mangling works, and it helps us to understand what goes on the next couple of slides. So if we've got print hello world and we want to see what the SIL is like, we can pass it with emit SIL. And emit SIL then generates out the Swift intermediate language that looks something a little bit like this. We've got here at the bottom SIL at main, so we're defining a main function. The at convention C says it's going to be a C function, so we'll use C function semantics for being able to call it and reference it. If you don't put the convention C on the front, then it will assume it's a Swift convention by default. And then int32, unsafe mutable pointer of unsafe mutable pointer of int8 is again the way that we do car ** inside Swift. And inside the intermediate language, you then have a bunch of references for the data types that you're using, functions that you call, and then ultimately the code that looks in afterwards. When you're dealing with classes, we've got something like a class world with a function hello in there instead. What happens is when you dump that through emit SIL, you get not only the function, but you also get something called a SIL V-table. Now, this is one of the other advantages of having an intermediate representation for Swift, because there's no concept of a V-table at the underlying layer in LLVM IR. But in the Swift intermediate language, you can say, well, we've got a V-table. That's a virtual table lookup, which you use to find out what functions are associated with a particular class. And here we've got a SIL V-table for world, and inside world, we've then got our hello function, with, again, one of these gibberish signatures afterwards that we can use to see what's going on. The interesting thing about the function name that's defined inside here is we've got TFC for main 5 world 5 hello S0 underscore FT underscore NT underscore. The T underscore at the end of it are tuples, in other words, empty arguments, so we're not taking anything, we're not returning anything in this side of this function. Other places might have called it void, but it's called empty tuple inside here. But we have the main function, so this is within the main module that we're defining it. We have the class name, which is world, and we have hello. And this means even if we have another module with a class called world and a function called hello, we can distinguish between those two things as far as the generated output is concerned. Probably wouldn't make sense if you had a lot of different modules with those things in there, but it at least allows us to have those concepts defined within the SIL. Now, this also highlights something called default arguments. Default arguments are things like print, where the separator is going to be the empty string, and the terminator is going to be the new line character. What happens on the underlying Swift code is that whenever you call a Swift print function, it has to evaluate what those defaults are if you haven't passed it. So if you're calling print without any extra arguments, then it will access those default values. And the ways those default values are presented is by another function. So when you call Swift print, what happens is you get this function here. This is the signature of the Swift function itself. There will be a function to get default argument of argument 1 and the default value of argument 2. So when you call a function to be able to do Swift, then you'll see a couple of additional functions being called prior to your Swift call coming up, and they're essentially evaluating what those default arguments for those two things happen to be. So we've got Swift print default argument 1 and Swift print default argument 2, which get compiled in. So if you've got something in Swift that looks like print hello, then actually what it looks like is something along the lines of let separator equals swift.print.default argument 1, let new line equals swift.print.default argument 2, and then call print with those 3 values inside. So that's how you get default arguments encoded inside SIL. Errors are handled in much the same way. Obviously, we've got error handling within Swift now, where you've got the throws and the try question mark and the try exclamation mark type things. Most of those, the way that they boil down to is quite similar to the way optionals work. So essentially, you have a function, and instead of returning out one value, it returns back two values. If you ever had to look at any Go code, you'll see that they've always got these OK, fail assignments inside there. Swift is doing the same thing, but it's a load easier to be able to write in Swift than it is in Go. So the way that you get the tuple back is that you get the ordinary result and then a pointer to an error code. And if the error code is non-null, that means an error is achieved. And if you've got something like a try exclamation mark, what it will do is it will check to make sure that's null, and if it's not, it'll go to an undefined function. So here, when we've got some function that returns a 32-bit integer, but it throws an exception if something happens, if you do try question mark with some function, then what it will do is it will do a tuple assignment, effectively, of OK, fail equals some func, and then it will return, if fail is empty, the optional value of the return result, otherwise it will return nil. And that's essentially what the compiled code is generating under the covers. If you use try exclamation mark with that, then you'll get return fail equals null. If it is, it'll return the OK value. Otherwise, it will throw fatal error. And fatal error just throws an undefined value and then causes the program to abort. If you've got a do with the try and catch on side there, then essentially it will work in with the goto so that it jumps to the error handling code instead. So I wrote this thing called SIL Inspector. I was going to do a demo of it. I'd be happy to show you the demo afterwards, but given that we're running out of time and my laptop doesn't plug into the projector, you'll have to take those miniature screenshots for being able to have a look at that. Unless... Which app do you want? I've been trying to see. Or we can... I think we might have time. You think we might have time? We are 5 minutes behind the schedule time.
All the programs around the world. Am I going to get a pocket knife to get all these? You cannot unplug from it. Like it's completely...
I've got a VGA instead.
Right, okay. Hang on. First of all, where's the HDMI cable?
It is here.
The HDMI cable, yeah. Right, okay.
Fun stuff presenting from one of these things. You just can't see the next slide ahead, which makes it a little bit more of a challenge.
Display board?
Yeah.
Yeah. There we go. I'm going to bring a penknife and chop these things off at one point.
I was asked the question, do you want to try your laptop beforehand? And I said, no, I'll be fine. What could possibly go wrong? Still, we got there in the end. Okay, so the traditional Hello World program. This is SIL Inspector. This is the program that I mentioned on the presentation. You can download it and you can play around with it to your heart's content. But essentially, I've got to print Hello World inside here. And I've got some tabs along the top which you can switch between to be able to see the various different stages of the SIL parsing. So if we have a look at the abstract syntax tree, you get this thing with a whole bunch of parentheses inside there. I don't know what it is with Apple. First they went with the square brackets, now they go with the round brackets. They're running out of brackets to play around with. But this is actually Lisp. So if you know about Lisp, then you can understand and read this. Most people don't know Lisp. But essentially, this is a tree-based representation. So at the top level, we've got our source file, then we've got code declaration, then we've got a brace statement, we've got a call function, blah, blah, blah. And somewhere down at the bottom, we've got our print call that we're invoking inside there. Now, you can actually render this into a tree, and there are tools within the LLVM space to be able to render that if you want to. But you can do the semantic analysis on that parse, and that really dramatically shrinks down the size of the tree. So once you do the parsing inside there, it's done the lookup of the types to make sure the types are okay. It's then converted in inline things that can be converted in inline. And as you can see down here, it looks a whole lot more readable. But you can have a look at the SIL, the Swift Intermediate Language for this. So this was the main convention that I showed beforehand. There is a lot of rubbish inside here. So if you go down here, it does actually look like most of it is gibberish, which to a certain extent it probably is. But what you can have a look inside is you can have a look for Hello World. So you can have a look down at the bottom, and we've got our UTF-8 string of Hello World inside here. Now, the way that the Swift Intermediate Representation works, and for that matter, LLVM works, is that you've got a whole bunch of arbitrary types that you can assign variables to. So the stuff on the left-hand side, the %13, %14, %15, and so on, those are all like temporary variables which are just going through. LLVM works on the assumption of only a single value is assigned to a single variable name as the code execution goes, and so all of these things are just incremented as within each function that you deal with. So we've got a hello world string literal inside here. That's at number 14. We've then got references to things like the pointers for setting it up and the functions for being able to create a new string from that object. And then ultimately we end up with these apply blocks. And these apply blocks are function calls. So in this case, we're calling the thing that we got from %12. %12 inside here is a function reference for creating a new string instance. Where's the apply gone? I've lost it again now. And then we've got 4 arguments inside here. So %14 was the string literal that we passed in. %15 is the second argument, presumably length, because we've assigned that to be 11 up here. And then %16 is -1, maybe because we don't need to do any conversion inside there. We then store that string once we've done the casting for it, and then we've got this function reference down here with the print command. Now, all of this looks complete gibberish, which is why you've got that demangle option that I talked about. So when you click demangle, suddenly it starts to make a whole lot more sense. And realistically, I can make it look like this program is really cool, but actually all it's doing is it's running a program, taking the output and whacking it in an NS text field. Down at the bottom left, which there's no hope in hell of you being able to see from back there, but if you run it, you can have a look at it. That's actually the command that it's running, so that you can just copy and paste it and see the effect with your own Swift code inside. So we've got our function inside here with our argument. We've got a print function here of %19. And what that's doing is that's calling the argument for default argument 1. %20 is calling the function for default argument 2. That's the separator a new line. And then it's being able to invoke down at the bottom the print for the apply function here. So the apply is actually calling us with %20 and %22. That's essentially the string that we're calling, the terminator and the separator and the new line character afterwards. The SIL comes in 2 forms. It comes in what's called the raw form, which will say at the top SIL stage raw, and a canonical form, which will say at the top with, if we get it up the top, there's quite a lot of it, which is why it's handy having something to be able to page through it. There we go, SIL stage canonical. So what the difference between the canonical stage and the raw stage is that the canonical stage then has more things linked in with it. So in this case, we've got swift.process._argc. That's a global variable that has the arguments, the argument count and the argument pointers for being able to do things. You'll end up with this global init thing. That global init thing is basically a one-off call, and it changes from Swift version to Swift version. But if you Google for that version, you'll find hundreds of people's source code where they've checked this in for some reason. And there's various other processes like Swift process, unsafe arg is where it stores the arguments, the car star effectively of Swift. And then you can go through. So the best way of finding these things out is to actually have some functions or things that you want to be able to deal with. So we can have an add function, which takes a couple of arguments inside here. Nothing spectacularly exciting. We're just going to be able to add them together. Slightly more interesting than hello world, but frankly not much. And then we can call it in our function to see what happens. So when you have a look inside the stage, one of the nice things is if you play around with constants, you can then relatively easily search for them afterwards. You can also search for add to be able to pull things up inside here. So here we've got main.add. So when you have something in the interpreter or you have something within the evaluator that's here, it goes into a module called main. If you had module on the top and you separated things out, then you'd see the module name on the top there. But main.add is the one that I've just written. We've got a function reference inside it. We are creating down here a couple of values. So we are, where's the 3 and 4 gone? We've got an add function here. So this is the implementation of the main.add function. Inside, and then we've got the code in here. So this BB0, nothing to do with the robot in Star Wars. This is actually a basic block 0. So the way that functions get chunked up into output with SIL is things get loaded into these basic blocks, and then when you're doing for loops and jumps back, they use these basic blocks essentially as labels to be able to jump back inside here. There's also something handy called debug value. That's useful for Xcode so that it can see what the value of these arguments are when it's stepping through them. They play no real relevance in the application runtime. And then inside here, we're getting hold of the add. So add, you may not know, is an infix function in Swift. Swift.plus is the name of that function. So we're getting hold of the function reference here as %4, and then we're doing apply %4 with these 2 arguments. So %0 and %1 being the 2 functions that come back inside here. All highly exciting, and we call it with 3 and 4 inside there. canonical one, you'll see that there's a few things more that it's doing with setting up the arguments inside. But you can actually drill through and then see the LLVM IR. So this is what the intermediate representation is once it's lowered out of SIL. And you can see inside here we've got our add function with 3 and 4 inside here. So this is where it's called %7 is where it's calling our addition of two arguments inside there. And if you wanted to, you can then even step down into assembly. So you can then see what it's down inside. Not particularly exciting. You may not be particularly surprised to know that there is an add instruction. So here we're putting 3 into EAX. That's the first argument. For some reason, we're putting it into AX and then moving it from EAX into EDI. It's an interesting optimization trick. And then we're doing the same thing with 4 as well. But if you turn on optimization, then it gets slightly more sensible and it does some more optimizations under the covers. And there's something as well, which is whole module optimization or link time optimization, which is when you do that and it figures out what the no longer reference fields are and flags are. And eventually it will then realize that you're not doing anything of any particular excitement. And inside here, you'll find it's actually just returning 0 because we're not doing anything in our program once we optimize everything out of it. Now you can also experiment with this and see what this would look like if you had it in a class. So you can have a look down inside there. Let's get the optimization off so it's not going to lose it completely. And then you'll see down at the bottom we've got our V-table. So our V-table for the class world is it saying the class world has got an add function. The add function is located here in the world add !1 label identifier. And there's also a deallocator and initializer as well, because when you have classes, you've got initializations. Anyway, this is quite a fun tool for being able to play around with. You can put a simple bit of source code inside the source tab, and then you can step through the various stages and see what they like. And if you want to do this via the command line as well, then down on the bottom left, you can see the command that you can run to do exactly the same thing. Anyway, that's SIL Inspector, and I hope you've enjoyed the talk. Thanks very much.
Would you like to take a couple of questions?
I'd like to have a couple of beers, but we could always combine the two. Yeah, happy to take any questions if anyone's got any.
Around the mic, one over here.
What layer is the endianness handled in terms of like order?
Yeah, good question. What's the endianness of the code itself? Actually, the way that the Swift intermediate representation works is that it defers to something called built-in. So at the top of each of the SIL files, you find that you've got this import built-in operation that will then connect it with the underlying platform implementation. So down here, we've got SwiftInt 32 and SwiftInt 8. Those are 32-bit and 8-bit characters, but you'll see there's also references to these built-in int 32 as well. So whenever you see a built-in, that's actually using the native platform's endianness for being able to do its representation and platform sizes as well. Now, the SIL code is actually 32 or 64-bit specific, so that when you compile it and you spit it out, there may be some optimizations that are done based on assumptions of endianness. But notionally, at least, there's not too many things within your Swift program that's tying it down because the built-in acts as the sort of shim between you and the operating system. It's kind of like the way NS integer works on Objective-C. It'll either be a 32-bit or a 64-bit integer based on what it is. And the built-in allows Swift to be able to sort of dynamically switch when it's compilable.
So, just a follow-up. So if in the event, Android ever adopts Swift as well, so in that case, given the architecture, then the built-in for that, it could be something else. As far as the endianness goes.
Yes, so it's certainly the case that the generated SIL can have some assumptions about it. And in fact, down at the bottom, I think, where's it gone inside here? Or was it in the IR? When you have a look at the IR, there's a list of attributes about the functions that says what the data type happens to be, what the linker options were, and so on. And that will really contain the sort of information about what the attributes of that particular program were. Interesting you mentioned about Android, because there was a pull request that has been merged into the Apple repo that allows Swift to be able to build on Android. I think we're still quite some way from then taking that to fully fledged applications and Android as well, but it's certainly moving in that direction.
Yeah. How does SIL compare to things like Diana and stuff like that?
Good question. What's Diana?
It's the old ADA intermediate language, distributed intermediate attribute notation for ADA.
Well, I've learned something new already today. The honest answer is I don't know. The idea of having intermediary stages or intermediary languages is certainly not a new one nor unique to Swift. I think what Swift has done for debugging purposes or for ease of maintenance is that it has exposed some of those intermediary steps of the pipeline generation, which then have found either inspiration in other languages like Rust's mill, or simply make the optimization steps a lot easier. When Swift came out, it didn't have the detailed level of SIL, although there was some in Swift 1.0, but it was originally anticipated as being essentially a proof of concept. Can you read it and check that to make sure your optimizations made sense rather than necessarily an end user one? But even things like GCC has different intermediary representations. One of the advantages of having an intermediary language like SIL is that there is a bit of a gap between what the source code says, which is what you traditionally end up with if you deal with something like the parse tree of a particular program, and then the kind of optimizations that you could then do for the intermediary language. So one of the reasons why Rust cited moving towards that intermediary language was they had Rust has got a lot of memory borrowing semantics. So in the same way that Swift and Objective-C does reference counting, Rust does make sure that there can only be one mutable owner of a particular reference at one time. And because they were trying to do that over the AST, they found it very difficult. But by moving to an intermediary step, they could then essentially aggregate for loops and while loops and so on, all into essentially goto with back branches, things that they wouldn't want to expose in the upper level language, but then made the lower level language a lot easier to deal with. So I don't know how well it compares specifically to Dyna, but I know that this is a common pattern that you'll see in other languages and other tool chains as well.
At what point does the type checker get run, and where is the type information encoded? How far can we take it through all those translations?
Yeah, so it's a good question where the type information gets done. But when you parse the abstract syntax tree, what it's looking for at this level is really just, is it well formed? Do the parentheses match up? Is func an expected keyword at this point? And it's not until it goes to the sort of resolved parse tree that then the annotation types are kicked in. So you'll see here we've got types being added. If I go back, we've got the type being the world type inside, and when we go to the parse type, then that information is removed because it's no longer needed as far as that part of the parsing tree is done. How far that then flows through, when you go into the Swift intermediate language, what you'll find is that each of the functions has got a collection of references to type. So we've got here on %1 an allocation ref, so that's the alloc, the creation of memory. We've got a function reference to the main world in it. We've got the deallocating, well, not particularly exciting, I guess. But what happens is each of the meta types, the things that you used to be able to get from the mirrors, all of that information is available within the SIL. And so a lot of optimizations use that kind of information to then know if you're dealing with something. At the end of the day, something like an optional int and an int looks much the same at runtime. An optional int is simply an int with an extra boolean attached at the end of it. So the type information is useful to know how large those structures are and how to unpack them and how to do the implicit conversions from one to another. Okay.
Okay, I think in the name of fear, we should probably end there. So a round of applause for Alex. Thank you very much.
Thank you.